Whew. Nothing like a good morning in the morning to get your heart rate up. Heart rate, what is it? Let me check mine. Mine is 5. No. 22. Wait. 54. Now, of course, none of those numbers make any sense unless I have a time to go with it. So we never talk about just how many beats you counted, but it's got to be a beats per minute. And what does that have to do with chemistry? Well, meet me back in the classroom and we'll talk about it. Okay. Chemical rate of reaction. First of all, what is a rate? A rate is something that you are measuring in terms of how fast it's going. So for example, we can talk about beats per minute. And for heart rate, that makes a lot of sense. If you're talking about engine speed, it's revolutions per minute, RPM. If you're talking about your speed in a vehicle, it's your kilometers per hour. It doesn't matter if you go 80 kilometers. It matters if you went 80 kilometers in 30 minutes and 60 minutes or in 120 minutes. That's going to change your speed, your rate. For a reaction rate, we want to know how fast the reaction is going. Well, how do we know how fast? Well, it's about, a reaction is producing a product. So we want to know either how fast the product is being produced or how fast the reaction is being, reactant rather, is being consumed. Either one of those is going to tell us our rate of reaction. So if you're talking about even dissolving something, which isn't a chemical reaction, how fast is your solute disappearing? Now, in terms of our chemistry, we can either look at the rate of reaction with respect to the reactants or with respect to the products. And we're going to be looking at the concentrations. And we use these square brackets to denote concentration. And that's usually going to be in moles per liter. Although we do need to understand that it doesn't have to be in moles per liter. And our time is often going to be in seconds because reactions tend to go kind of quickly. Again, doesn't have to be. As long as we're measuring, have some way to measure the amount of product or the amount of reactant and the time, then we can turn that into a rate. However, our most common one is going to be moles per liter per second. And we'll find out in class that there's a couple of other ways we can represent that moles per liter per second. So it doesn't always have to be the mol/L/S. All right, really important for you to understand as part of the concept. It's not really going to work into our math or work very often, but the rate is not a constant. As much as we love straight lines, and they make our lives so much simpler if we can find slope and intercept and all that, this is not going to be a straight line. However, it's not going to make that much difference to us. At the beginning of the reaction, you've got a lot of reactants, and those reactants are able to form products and very few products. So your reaction rate, consumption of the reactant, or production of the product, that can be very high. Whereas, as the reaction continues and progresses and moves to the end, the reactant amount gets quite small, and the product amount can get quite large, and the rate tends to flatten out or trickle off and get quite small. That's not going to make a whole lot of difference to what we do. I just want you to be aware that the rate of a reaction is not constant. There may be times, between this point and this point where it's fairly constant, but it's never going to be constant. Well, I said you could do a reactant or you could do a product. Does it matter? No, it doesn't matter, because as long as it's within the same reaction, it's going to be related. So if you look at this reaction that I've given here, where the stoichiometric balancing coefficients are all 1, 1, 1, and 1, if I had a situation where I knew the reaction rate with respect to one of the reactants, in this case methane, CH4, then I could also confidently say that the reaction rate with respect to the other ones, whether it's the other reactant being consumed or the products being produced, because everything is 1 to 1 to 1 molar ratios, the numbers will all be the same. So if I want to measure the reaction rate with respect to one, but report it with respect to another, I can do that. But I know what you're thinking. You're wondering, well, hang on, very often the reaction balancing coefficients are not all the same. They're not all ones. What do we do then? Then we do something that looks a bit like stoichiometry, but it really isn't stoichiometry. So if we take a reaction like this one, where obviously the balancing coefficients are not the same, however they are related. So for every 1 mole of nitrogen, I need 3 moles of hydrogen, and for every 1 mole of nitrogen consumed, 2 moles of ammonia, NH3, are produced. If I know the reaction rate with respect to the production of ammonia, NH3, I could then calculate the consumption of nitrogen, or the rate of consumption of nitrogen. And I would do math. And it would look something like this. Now the first term there, the delta N over T, that's just our rate. That's just how we express the rates. The rate of change of concentration of nitrogen as time passes, that's the rate, is going to be the rate with respect to the one I know, and then times the ratio of how they're related in a balanced chemical reaction. And I would get that number. And if you want to double check the math, please do, encourage that. If I wanted to know the consumption with respect to hydrogen, now this is going to look a little uglier because it's 2 and 3 are my balancing coefficients, but it's not going to be any different. It's going to be exactly the same thing, the rate that I know, and then how those two things are related in the balanced chemical reaction. Too easy. And I get that number. So as long as I know the rate with respect to one thing in a reaction, I can calculate all the others. I need to, no, we're good. All right, to wrap it up, if I know a reaction, and I have it balanced, and I always want to work with a balanced chemical equation, if I know the rate of one, and I divide it by its coefficient, and I know the rate with respect to the other divided by its coefficient, and the rate with respect to the other divided by its coefficient, and it could keep going if I had more, those numbers will all be equal. Now how does that help? Well, if I start looking at just taking two of those terms, and rearrange them, I'll actually end up having on my paper something that looked a lot like the previous slide, where I was using one to calculate the other. That's about it in terms of rates and how we work with them. We need to figure out how to measure them, we need to figure out how to express them in other ways, but in terms of what a reaction rate is and what it means and how we express it mathematically, that's all there is to it. We'll see you in class.